Hello, my name is Alex Forensic. I am a postdoctoral researcher at UC San Diego. The title for my talk today is Corundum, an open, full-stack optical networking framework. Our research group at UCSD focuses on optical switching for data center networking applications. Over the past few years, our group has developed a number of experimental networks that utilize a variety of optical switching technologies. We build these systems at a scale large enough to provide interesting measurement results. To facilitate this, we need to use as much commercial hardware as possible. However, commercial hardware is generally not designed with optical switching in mind. As a result, we run into roadblocks occasionally. One of the biggest roadblocks is the ability to precisely control the flow of data into the network. The ability to precisely control packet transmission from servers has many applications, including rate limiting, flow control, congestion control, TDMA, circuit switching, etc. However, sub-microsecond control is not feasible in software. In order to get that level of precision, it must be implemented in hardware. Unfortunately, there is very little support on existing commercial NICs for this type of feature. Commercial NICs generally provide a very limited number of queues and only provide limited control over the rate at which those queues can drain. Commercial smart NICs can open up some additional possibilities, but in many cases, smart NICs have architectural limitations that preclude this type of control. However, it is possible to do on an FPGA. The only issue is that up until now, there have not been any high-performance reference designs that can be extended with this type of feature. And this is where Corundum comes in. Corundum is a reference, open-source, FPGA-based NIC that supports many different FPGA platforms. It provides a network interface similar in performance to a commercially available NIC. It enables the implementation of additional hardware features needed for circuit switching and in-network computing. First, an overview of the high-level features of Corundum. Corundum is an open-source, high-performance FPGA-based NIC that supports multiple 10G, 25G, and/or 100G Ethernet ports. It uses a fully custom, high-performance DMA engine to support operation at 100 gigabit per second line rate, along with a Linux driver to connect to the Linux kernel networking stack. Using thousands of hardware transmit queues coupled with customizable per-port schedulers, Corundum can control data transmission on a per-destination or per-flow basis. These schedulers, in combination with IEEE 1588 PTP time synchronization, enable microsecond precision TDMA. This TDMA functionality provides a very powerful 5-layer BER measurement capability for characterizing optically switched links. The core Corundum data path is quite high performance and can support transfer rates of over 60 gigabits per second for 1.5 KB MTU frames on a 100 gigabit per second link. The plot on the right compares the performance of the Corundum NIC to a commercial Mellanox ConnectX-5 NIC. This data was collected using a variable number of iPerf processes to load the link in both the transmit and receive directions simultaneously. We believe that improvement should be possible with further optimization of the driver. Additionally, Corundum can provide TDMA performance of 2 packet lengths, either 1.5 KB MTU packets at 10G or 9 KB jumbo frames at 100G. All of this is open source on our GitHub repository that is linked here. At UCSD, we are going to be connecting the Corundum NIC to an experimental optical switch called the rotor switch or pinwheel switch. This switch is based on free space optics, and it uses diffraction gratings that are patterned onto what is essentially a hard drive platter to select between several different network configurations. As the disk rotates, it will select one of 4 different network configurations in sequence. Here is a render of the disk, and here is what it looks like as a complete system before we install it in the rack. In this case, we have 5 fiber arrays, 1 central array for all the input and output connections, and 4 additional arrays that form the network configurations that we can choose from. This switch technology provides very good optical parameters, and it can scale to a very large number of ports while providing microsecond scale switching. On the flip side, the switch is not particularly flexible, with many important parameters baked into the switch design during manufacture. This is what the switch looks like when it is installed in the rack. There are 11 servers in the test setup. 9 contain alpha data FPGA boards that are populated with 40G QSFP plus PSM4 transceivers. The 4 channels of the transceivers are used independently providing each of the 9 hosts with 3 connections to the optical switch. In this case, we are using the switch to emulate 3 separate switches with offset schedules such that only one switch can reconfigure it at any given time. Since Corundum is built on an FPGA, we have direct access to the physical layer transceivers. This enables us to perform very low-level characterization of the links through an experimental optical switch. This method works by sending a continuous pseudorandom bit sequence through the link and counting the number of bits that got flipped at the receiver. Coupled with PTP time synchronization, these bit errors can be localized in time and related to the switch configuration. The result is a heat map like this one. In this case, the heat map represents one complete revolution of the pinwheel switch disk, comprising 54 separate gratings or 3 network configurations repeated 18 times. Each row in the heat map represents one grating with a dwell time of 222 microseconds. The heat map is not aligned with the disk position, so each row actually shows parts of 2 adjacent gratings, including the transition in between. From the heat map, we can see the physical layer switching time, comprising not only the switching time of the optical switch itself, but also the AGC and CDR lock times at the receiver. Since this measurement is performed with continuous PRBS data, it does not include 64B 66B frame sync from the line code or NIC transmit timing accuracy. Some of the transitions are significantly extended, indicating optical power variation. We can also see some localized defects in the gratings. This technique enabled us to identify fabrication issues in the switch disk that can be corrected in the next version. Looking at the heat map a little bit closer, it is clear that not all of the paths through the optical switch are completely unusable. In this case, one of the 3 configurations shows reasonably good performance. With Corundum set up to enforce a TDMA schedule over this path, we were able to successfully run iPerf through the pinwheel switch. This is the first time that we have been able to run a standard unmodified Linux application through an experimental optical switch. On top of the core Corundum design, we can build hardware to support higher level features. This logic can take the form of a shim that sits in between the core Corundum data path and the Ethernet MAX. This capability can be used to evaluate novel features, including hardware protocol implementations and components for in-network computing. One possible application for a hardware shim is circuit switch emulation. Emulation is necessary to permit system-level experiments to run in parallel with the development of experimental optical switches. Emulation can also be used to explore the impact of optical switch performance characteristics independent of the switch technology. Packet switches route packets based on headers, and to do this they must examine every packet as it arrives at the switch. Circuit switches, on the other hand, operate on the level of links, and they rely on packets arriving at the switch when it is in the appropriate configuration. Packets that arrive at the switch earlier or later will end up taking a different path through the switch. In this sense, circuit switches route packets based on time. The circuit emulator shim works by encapsulating packets with an additional set of headers based on the arrival time of each packet. The packet switch then routes the packets according to this new set of headers. The headers must be removed on the receive path to restore the original packet. One minor complication is the need to share the link to the packet switch with control traffic such as PTP. A simple solution to this is to use MAC VLAN or similar to provide a virtual interface with a different MAC address for control traffic, and then bypass the shim based on the source MAC address. This is a block diagram of a circuit emulation shim. Each NIC port gets one set of encapsulation and decapsulation logic that sits between the NIC data path and the Ethernet MAX. The encapsulation logic will also be connected to the PTP hardware clock in order to implement the circuit schedule. It is also possible to install additional shims between the NIC data path and the circuit emulator shim. Current Ethernet line protocols are not designed with circuit switching in mind. As a result, it can take quite a long time for a link to recover after an interruption. For 10G and 25G links without FEC, only clock data recovery and frame sync are required, which generally takes around 10 or 20 microseconds. For 40G and 100G links, lane bonding is required, and it takes around 200 microseconds for a 100G link to obtain alignment marker lock across all 20 virtual lanes. When forward error correction is used, the situation is even worse. Achieving FEC block lock on a 100G link takes milliseconds. For efficient operation in a circuit switched environment, the line protocols need to be revisited. Otherwise, the speed of a fast optical switch will be wasted on guard delays. For very fast switches, burst mode receivers and fast frame synchronization techniques are required. Lane bonding and FEC will require additional modifications to the line protocol and possibly knowledge of the switch schedule at the physical layer. Since Corundum provides direct access to the transceivers, it is possible to implement custom line protocols and evaluate them in concert with an optical switch in a data center environment. Corundum was never intended to be just a research project. The goal is to develop an ecosystem and provide a complete prototyping platform that includes a high-performance data path and device drivers that are extensible in both hardware and software. Additionally, Corundum will include features to support scaled-up deployments, such as in-band firmware updates over PCI Express, transceiver access for debugging and physical layer development, MAC address readout from on-card EEPROM, and other useful ancillary features. Corundum supports a range of FPGA devices and platforms, currently encompassing Xilinx Virtex 7 through UltraScale Plus. We plan to add support for SoC devices such as Zinc, where the ARM core can act as the host instead of an external CPU connected over PCI Express, as well as FPGAs from Intel. Currently, Corundum has only a device driver for the Linux kernel networking stack. We plan on extending this to include DPDK, which permits the use of user-space networking frameworks for improved performance and flexibility. Additionally, we are working with Xilinx Research Labs to figure out how Corundum can fit into OpenNIC/NetFPGA 2020. The current development roadmap for Corundum looks something like this. We would like to improve the performance of the current Linux driver through additional optimization, as well as develop a driver for DPDK. Other software APIs, such as MPI and libfabric, are also under consideration. On the gateware side, there are a number of improvements to be made. Variable length descriptors can improve PCIe link utilization. Additionally, they are much more expressive, enabling extensive metadata support, which is useful for interfacing with hardware accelerators. For applications involving virtualization, implementing SRIOV can significantly improve performance. Ancillary features including in-band firmware updates and transceiver access will support the use of Corundum in larger testbeds. The ultimate goal is to provide a prototyping platform that covers the entire networking stack, from the physical layer all the way up to the application. At this point, we're looking for additional contributors. If you think Corundum is interesting, and you know a thing or two about DPDK, the Linux kernel, or FPGA development, let's get in touch. Similarly, if you have some ideas for applications that could take advantage of Corundum, hop on the mailing list and let's bounce some ideas around and figure out how to implement your idea with Corundum. Here are some links to the Corundum repository on GitHub as well as the mailing list. Go check it out. Thank you very much for your attention.